Okay, so we're going to be doing optimization. So we have a rectangle and it has a base on the x-axis and the top two vertices are on the parabola y equals 12 minus x squared. What is the largest area the rectangle can have and what are its dimensions? Okay, so first you got to deal with that parabola. So the parabola itself is the quadratic that's been reflected, so it opens down and shifted up 12. So the vertex is right here at 0, 12, and it opens down like this. Okay, now I didn't graph it exactly the way it should look, okay, because I wanted to have enough room to draw my rectangle. Okay, now the rectangle is going to be inside with its base here on the x-axis, okay, and the two top vertices touching the parabola like this. Okay, what is the largest area the rectangle can have and what are its dimensions? So again, when we're doing optimization, we need to come up with our primary equation. So a primary equation is whatever we're optimizing. And since we're trying to find the largest area, area is my primary. And the area of a rectangle is length times width. Okay, that's my primary. Now, let's label my parabola, or sorry, my rectangle. So this is my length, this is my width. Okay, now there could be a bunch of different rectangles. This isn't the only possible rectangle. There could be a rectangle that looks like this. Okay, there could be another rectangle that looks like this. Could be this rectangle. These are all possible rectangles. Okay, now which one is it? Well, I don't know. But I do know that since this vertices here, no matter where it hits, it is the coordinate xy. Okay? Now, I should have gone back first. So let's just focus on the blue one. So this coordinate, of course, is xy. Now, that means xy, from origin, this right here is x, and this right here is y, which means that my width is y. So this distance right here is y. No matter where it hits on this parabola, which one I use, the width is going to be y. The length, since this part is x, this part over here is also x. That means my length is 2x. Okay? So based on my picture, I can now rewrite my area in terms of x and y. So my length is 2x times my width, which is y. Okay? Now, where does this y value come from? Okay, what is limiting? Because that's my secondary equation. My secondary equation is whatever my constraint or my limiting factor is. And in this case, what's limiting this rectangle is my parabola. Specifically, y equals 12 minus x squared. That is some people call it your constraint. I call it my limiting factor, which is the secondary equation. In optimizations, basically the steps are you find your primary equation, you find your secondary equation, your constraints. You use your secondary equation to plug into your primary to get it in terms of one variable. Then you're basically doing a first derivative test where you find the derivative, set it equal to 0, find your maximums or minimums, your critical points, and you check your endpoints. Okay, and those should give you your maximums or your minimum that you need. Okay, so here, since I'm using my secondary to plug into my primary, I can plug this y here in for that y there, which gives me my new area equation, which is 2x times 12 minus x squared. Simplify, we get 24x minus 2x cubed. Then we take the derivative. So 24x, derivative is 24, minus 2x cubed, which is 6x squared. So that's my derivative. set it equal to 0. So 24 equals 6x squared. 4 equals x squared. And then x equals 2. Okay, so x equals plus or minus 2. Now, it can't be negative 2 because you can't have a negative length, so x is positive 2. Okay, well, if x is positive 2, since my length is 2x, that means my length is 4. My width is y, which is 12 minus x squared, and we use that to find our width. So it's basically 12 minus 4, which is 8. So my length is 4, my width is 8, and the largest area then, since my area is length times width, it is 4 times 8, which is 32. So those are my answers. Okay? So again, we're doing the exact same thing over and over again with optimization. Find your primary, you find your secondary, you plug your secondary into your primary, find the derivative, set it equal to 0 to find your critical points, and of course, basically, our x values could be anything from 0 to, in this case, wherever the x-intercepts are, which would be like 3 something, 3.4 or something like that. You just have to find the intercepts. Okay. Now, I'm going to use a separate video for the next one.